Okay, greetings everyone, and welcome to the MAA-AMS-SIAM Gerald and Judith Porter Public Lecture. My name is Ruth Charney. I'm president of the American Mathematical Society, and it is my honor to introduce today's speaker. This is the final invited lecture of JMM 2023, and so I want to thank you all for coming to JMM and for staying right to the bitter end. So the Gerald and Judith Porter lecture series was established through the generosity of Gerald and Judith Porter as an opportunity to present current topics in mathematics to the broader community. It is a great pleasure to introduce this year's speaker, Professor Bernd Sturmfels, director of the Max Planck Institute for Mathematics and the Sciences in Leipzig, Germany. Professor Sturmfels received his doctoral degrees in 1987 from the University of Washington and the Technical University of Darmstadt. He served on the faculty at Cornell University before moving to UC Berkeley as a professor of mathematics, statistics, and computer science. In 2017, he was appointed to his current position as director of the Max Planck Institute. He also holds honorary professorships at the Technical University Berlin and the University of Leipzig. Professor Sturmfels' research spans a wide range of mathematical fields, including combinatorics, commutative algebra, algebraic geometry, and applications to statistics, optimization, and computational biology. His work in these areas has earned him an impressive array of honors and awards. I was told to keep this introduction short, so I'm not going to attempt to list them all, but let me just mention a few. He is the recipient of a David and Lucille Packard Fellowship, a Humboldt Senior Research Prize, a Sarlo Distinguished Mentoring Award, and a Birkhoff Prize in Applied Mathematics. He is also a fellow of both the AMS and SIAM. And perhaps most impressive, he has mentored 60 doctoral students, authored 11 books, and approximately 300 research articles. So I am very much looking forward to today's Porter Lecture, entitled The Quadratic Form Revisited. Please welcome Professor Bernd Sturmfels.
Yeah, thank you, Ruth, for the very nice introduction. Thanks to all of you for coming at this late hour. So I'd like to show you some pictures in this talk and tell you about the quadratic formula and why, in my mind, the quadratic formula is the single most important thing you learned in high school. So suppose you have a quadratic equation, ax squared plus bx plus c equals 0. And let's think about this as some kind of a model, some scientific model. So x is an unknown quantity or parameter. And think about a, b, and c as measurements. So we're performing some experiments, and we're measuring real numbers a, b, and c. And this might happen many times. And the question is, how do we solve this equation for x? How do we express the unknown quantity x in terms of the measurements a, b, and c? Well, here's the answer, right? The teacher presents a formula, a general formula, and the poor students memorize this formula. That's usually how it works. Now, of course, some of the more clever students might ask the question, why do we solve this equation? So how do we solve the equation? Why do we solve this equation? Well, I don't know. No clue, right? The curriculum requires it. And besides, math class is totally boring, okay? So this is maybe back in 9th grade or at some point in your school career, many people had precisely this experience. So I'd like to discuss a little bit what's going on with this quadratic equation. Now, first of all, what is the formula? So here's the formula that these students memorize. So x can be written as a ratio minus b plus minus the square root. And in the square root, you have b squared. This looks like a typo, doesn't it? B squared minus 4ac divided by 2a. And the hero of today's talk is the discriminant. So the discriminant is the expression b squared minus 4ac. Now, what does the discriminant do? The discriminant discriminates. And in the context of this math talk, and the context of this math talk only, discrimination is a good thing. So I will talk about today about the discriminant and why, in this context only, discrimination is a good thing. What is the discrimination? Well, there's a case distinction. Either the discriminant D is positive, or it's 0, or it's negative. And it's positive says there are two real solutions. If it's negative, there are two complex conjugate solutions, no real solution. But if D were 0, then there would be a double root. But that doesn't happen, right? Remember, A, B, and C are measurements, and they're inexact. So it's a probability 0 event that we're in the middle. So D is either positive or negative. So these are the two cases that we're discriminating. And this is why the discriminant is so important. It tells us this distinction between these two cases. Now, at the risk of boring you, let me actually go over the derivation of this formula. So this is how you do this in high school, right? So you apply a sequence of transformations that are reversible. So first you subtract C on both sides, that you add B squared divided by 4A. Here care has to be taken that A is a non-zero. Then you form the square. You have A times a square is something on the right-hand side. And then, whoops, then you have take the square root. That introduces the plus minus. And at the very end, you subtract B divided by 2A. And that's where you have derived the quadratic formula. So by completing the square. Now, this works very nicely, right? So now if we make our measurements A, B, and C, we can rapidly evaluate the right-hand side and get an expression for x. Now, what happens if we have polynomials of higher degree? Right? So it could happen. We have a polynomial, have a model that doesn't have degree 2, but might have degree 4 or 5 or 6. Well, in general, then you will look for a numerical solution or some kind of symbolic representation of the roots. So then you get into more advanced ways of speaking about the roots and computing the roots. But of course, most models are not in one variable, but there will be many variables. There will not be just a single x. There will be x1, x2, many x's. And at that situation, you might have to do nonlinear algebra, Grobner bases, or numerical methods, numerical algebraic geometry. So all the things I'm going to say today are completely general, but we're starting point of departure here with the quadratic formula. Now, of course, in my mind, and I hope in your mind, math is not boring, right? Math class is not totally boring, but it's fun. But what is math, and why is it fun? Well, let me go over these three quotes, right? So Galileo said that mathematics is the language in which God has written the universe. Well, that's a pretty good motivation. Goethe, translated from German into English, said mathematicians are like Frenchmen. Whatever you say to them, they translate into their own language, and forthwith it is something entirely different. Right? So that's true, that is true, and I think that's a strength of mathematics, that we can take seemingly disparate topics from the world and translate it in a very concise, unifying language. But of course, ultimately, we have to give back. We have to be outward-facing, as we learned this morning. Bertrand Russell wrote that mathematics, rightly viewed, possesses not only truth, but supreme beauty. So I like to kind of make a pointer to beauty by showing you these pictures today. So there's this blue picture, there's the Rubik's Cube at the bottom, so I'm going to sprinkle in these pictures, and they are going to be my placeholders for supreme beauty. So let's start the supreme beauty with this cubic surface. So now down at the bottom, I had in blue an equation in 3 variables, x squared plus y squared plus z squared minus 2xyz minus 1 is equal to 0, right? So if you plot all the solutions to this will be a surface in the 3-dimensional space with coordinates x, y, and z. And this surface is this yellow-red shape. So this is called Cayley's cubic surface. Sometimes it's called the elliptope. So in the middle, in yellow, you have this convex body that looks like a samosa. So it's a blown up tetrahedron. You take a tetrahedron and you puff some air into it. But then at the 4 vertices, you grow out some red elephant ears. They go off in an unbounded way. And this red, yellow stuff together is this cubic surface. Supremely beautiful. Now, this object is actually the logo of the nonlinear algebra group at our institute in Germany, at the Max Planck Institute for Mathematics and the Sciences. Arthur Cayley studied this in the 1800s, and so this is known as Cayley's cubic surface. And for us, this is a symbol also of the connection to optimization, semi-definite programming, statistics, Gaussian random variables, lead to these kind of pictures, and I'll make a little bit of advertisement. So this talk also is an invitation to nonlinear algebra, and there's a book with this title together with Mateusz Michalek that was published the year before last. Continuing on the supreme beauty, let's go from surface of degree 3 to surface of degree 4. Here's another equation in x, y, and z, and if you plot this in 3-dimensional space, you get this blue surface. This blue surface has 16 singular points. There's the inner samosa with 4 vertices surrounded by a bunch of other ones. So altogether, there are 16 of these singular points. And this is known as the Kummer surface, named after another 19th century mathematician, Ernst Kummer. And this Kummer surface is actually a group, right? This is actually up to a 2-to-1 cover. This is an abelian surface. It's a group, and as such, it has applications in cryptography. So you've heard that elliptic curves are very important in cryptography. This is a 2-dimensional version as an elliptic curve. So there's a group structure. You can take 2 blue points, multiply them, and make another blue point. Supremely beautiful. So the objects I'm showing here in these pictures, they're called varieties. So a variety is a subset of R to the n that is the 0 set of one or more polynomial equations. So I have a bunch of polynomials, and the 0 set or solution set I'm going to call a variety. Well, one variety we saw at the beginning, right? We had one quadratic equation in one variable, and the variety is just 2 points on the line. And we started out with the formula for those 2 points. So now we're going up. We're taking 2 quadratic polynomials in 2 variables. Well, the corresponding varieties are pictured here in the plane. So we start out with a blue quadratic equation, maybe the circle, and this quadratic equation has 6 coefficients, a1, a2, a3, a4, a5, a6. In comes a second equation, maybe the green ellipse, and it has its own 6 coefficients, u1, u2, u3, u4, u5, and u6. So now there are 6 plus 6, 12 coefficients in the game. But of course, I can intersect them, and the intersection is these 4 points, and that's also a variety, right? So this picture shows 3 varieties, one green, one-dimensional variety, a blue, one-dimensional variety, and a red, 0-dimensional variety. Now, 2 quadratic equations have almost always 4 complex solutions. So this is Bézout's theorem, a special case of a theorem that's now 250 years old due to Bézout. If you have 2 curves in the plane, complex plane, then you multiply their degrees to count the number of solutions. Now again, our hero comes back. There's a discriminant, right? So there's a discriminant is a big polynomial or small polynomial. It's a polynomial in the 12 coefficients. There will be a polynomial in the 12 coefficients, a1, a2, a3, a4, a5, a6, u1, u2, u3, u4, u5, u6. And this discriminant discriminates. It specifies that a case distinction, there will be either 0, 1, 2, 3, or 4 red solutions. There will be the 4 points are either all real, but you can also see in the picture, just pretend the green ellipse slides to the right. At some point, the two left red points come together, there's a tangency, beep, they become a complex conjugate pair, then there are only two real solutions, and you slide the ellipse further to the right, and eventually there's another tangency, and the two curves have no more real intersection points, but there's still 4 intersection points. Now, how do we know in which case we are? Well, luckily, there's a discriminant, and here it is. So this discriminant is a polynomial in our 12 coefficients. It is homogeneous of degree 12, and it's a pretty small polynomial. That's 3,210 terms. Now, it's a little bit more difficult for a high school student to look at this, or let alone derive it with pencil paper, but it's still a polynomial. It still does exactly the same thing as our friend from high school. It distinguishes these cases. So the analysis as to which of these cases we're in is governed by the discriminant, and this discriminant is identically 0 precisely if the green quadratic curve is tangent to the blue quadratic curve. Okay, this is the discriminant. And so I like to tell you about these kind of discriminants, and this is the lesson to take home. They always exist, and they carve up the parameter space. Now we have 12 measurements. Remember, A1, A2 are the results of an experiment. These are measured real numbers, and then the nature, this discriminant will tell us about the nature of these data vis-a-vis the green, blue, red model that we are trying to describe here. Now, of course, maybe 2 conics are not enough. You can take many conics. So here's another picture from a classical geometry problem from the 19th century. So suppose you fix 5 blue conics in the plane, so 5 quadratic curves in the plane. So in this picture, you see 4 ellipses and 1 hyperbola, so 5 quadratic curves. And now we're interested in all red conics that are simultaneously tangent to the 5 given blue conics. Now, it turns out there are 5 degrees of freedom of specifying a conic. Well, we had 6 coefficients, but if I scale them all up and down, it will be the same conic. So if I multiply by 2 or by 17, I don't change the conic. So there are 5 degrees of freedom of drawing a conic. There are 5 constraints on the red conic. There are 5 constraints. Now, what kind of constraints? Well, this constraint, right? So I'm writing down this equation 5 times. So for each blue curve U, there will be one of these equations. This gives me a system of 5 equations of degree 12 in 6 homogeneous variables, and that algebra problem then we can solve, not by hand, right, but with the computer. And it turns out that the number of solutions is 3,264. So this is a famous number in the history of geometry. And here in small print, it says Jakob Steiner in the early 1800s, 1840, asked how many conics are there? Well, the answer is 3,264. But nowadays, we ask a slightly different question. We ask the question, if you give me your conics, so Tom, you draw 5 blue conics in the plane, find all 3,264, and this software down there will do that in well under a second. Okay, so you can try it out. It's an app. It was broken last week, but I hope it works again today. So if you get bored, you can try it out. So those are conics. So we talked about what happened so far in this talk. We talked about polynomials in one variable of degree 2. We did that in 9th grade. And now we looked at polynomials of degree 2 in 2 variables. Let's talk a little bit more about data. So the mathematics of data is very popular these days. Historically, this is called statistics. So this is an example I learned from an introductory statistics textbook in the UK. So in the UK, this is called football. Here it's called soccer. So recently, we had the World Cup. This is very exciting. And you can ask me how I got this injury. It had to do with the World Cup. So in this example, we're asking the following question: whether watching too much soccer on TV leads to hair loss. Right? Now, of course, every day in the newspaper, we learn that some behavior or some food has some certain medical consequence. Right? So does this cause that? So here we want to ask the question whether watching soccer on TV, makes you lose hair. Right? Okay, so we're going to ask 296 people, and we classify this into 3 states, right? So less than 2 hours soccer per week, medium amount 2 to 6 hours, and the real fanatics who watch more than 6 hours a week soccer in the last row. And then, people have full hair, medium hair, and then little hair or bald, right? And so, for example, 33 respondents had very little hair, and they also watch very little soccer, okay? Now, before we can ask about causation, we should ask about correlation. And the question is there a correlation between watching soccer and hair loss, just based on these data? Well, you look at this for a moment. Well, if this were perfectly independent, if these 2 random variables, so soccer and hair, if these are 2 perfectly independent random variables, then this would be a rank 1 table, right? This would be a rank 1 matrix, right? Because independence says the probability of being in a certain soccer state and a certain hair state is the product of those 2 states. And this means the matrix would have rank 1. But this matrix not only has not rank 1, all the 2 by 2 subdeterminants are strictly positive, right? So you look at this, and so this seems to suggest a positive correlation, and therefore the bold-faced question. Now, it turns out that there is a hidden random variable, is a mysterious, unknown hidden random variable, and well, this is an old example from an old British textbook. So at that time, in that textbook, gender was a binary random variable, okay? And so the study involved 126 males and 170 females. And now let's suppose we had the data separately for the men and for the women. Well, then the big table is the sum of these 2 tables. But in this contrived example, the male table has perfect rank 1, perfect independence, and the female table has rank 1, perfect independence, right? So therefore, this suggests a model that hair length is not independent from soccer, but is conditionally independent from soccer given the gender. So for fixed gender, we have independence, so altogether this suggests conditional independence. Now, here's the thing about statisticians. They're very fussy people, right? They never accept the null hypothesis. They either reject it or they don't, right? So, but based on this data, we cannot reject the null hypothesis, which says that this conditional independence model holds in this situation. Now, where is the variety? This is supposed to be about varieties and discriminant. Well, the model is a variety. So in algebraic statistics, the philosophy is statistical models are algebraic varieties. They're described by polynomial equations, sometimes inequalities. Now, what are the equations here? Well, first in words, so conditional independence of 2 ternary random variables. Well, this is the cubic hypersurface in R9 given by the vanishing of the determinant. Well, how so? Well, what's the rank of a matrix? Well, a rank 1 matrix is a matrix that's a column vector times a row vector, right? So this is a rank 1 matrix, right? Now, rank 2 matrix is the sum of 2 rank 1 matrices. Well, this is a rank 2 matrix. It's the sum of 2 rank 1 matrices, which means the determinant vanishes. So the 3 by 3 determinant of a rank 2 matrix vanishes. So this model of conditional independence is really given algebraically by a very interesting cubic hypersurface in 9-dimensional space called the 3 by 3 determinant. Well, now let's go out, collect data. So I have a data matrix Uij. So Uij is the counts I had, like 33. So this is the number of people with hair state I and soccer state J. Then we look at the likelihood function. This is the monomial P11. So P11 is the unknown probability to be in soccer state 1 and hair state 1. So we have these unknown probabilities raised to the known positive numbers that we get from the data. And what we like to do is to maximize this likelihood function. So in likelihood inference, we maximize this likelihood function. Now, very good. This, of course, how do we solve an optimization problem? Well, from an algebraic perspective, Whoops. Do you want the U's? So the U's are the data. No, so I'm taking the P, so the U, so Uij is the number of people that are in my count that have hair status J and soccer status I. Okay? Now, and then these people are independent. So you walk through Boston, you ask 300 people, and the assumption is that this is independent among these people, and therefore it's multiplicative. So P11 to the U11, this is simply the product, and this is called the likelihood function. So the likelihood function up to a global constant is the probability of observing the data that you did observe given the sample size. So you say, I'm going out in Boston, I'm going to ask 296 people. Well, there are many possible outcomes, right? But then there's the actual outcome that in your query you get, and this is the probability of seeing the outcome you did get. And you want to maximize that under the assumption that you're in the data. Well, this is an optimization problem. The critical equation is a system of polynomial equations in the 9 P's. Well, you analyze this, has almost always 10 complex solutions. But how many of them are real? The statisticians are not interested in complex solutions. They want real, ideally real positive solutions. They need to discriminate. They need to distinguish, right? How many real solutions are there? Where are the real solutions? Where is our hero that can do this? Well, that is the discriminant, right? The discriminant is a polynomial in the data, U11 up to U33, that discriminates the different cases, right? So in this space of all data, this 9-dimensional, this high-dimensional space of all possible data, there's some hypersurface given by some big polynomial in the U's, and depending where you are vis-a-vis this hypersurface, it tells you about the nature of the data. It's a case distinction. Now, I should maybe say a word about the philosophy here. Sometimes students ask, you know, what area of math is relevant if I want to go into data science? Or what area of math is, you know, should I study? Right? Well, the answer is your area of math, right? Any area of math is relevant for the study of data. And this has been, from a geometric point of view, so there are many different perspectives of this. So if you're a topologist and you look at this, then you will invent topological data analysis, right? Then for you, this is a topological space, and you're going to compute the persistent homology, and so on, right? Now, if you're a differential geometer, then you will look at this same object, this red-blue variety in 9-dimensional space, red-yellow variety, and you look at local differential geometric features. You look at curvature, you look at curvature tensors, connections, you know, Ricci curvature, and you will invent information geometry, right? Now, if you're a commutative algebraist or an algebraic geometer, you will either look at global equations, global properties or singularities, and you will invent algebraics, and so on, right? If you're in geometric group theory, you do something else on harmonic analysis. So the area of math that's relevant for data science is your area of math. Well, here is the picture we saw at the very beginning, and I just want to tell you what that is. So this is supremely beautiful. On the left, you see a 3 ellipse. So what do? We have 3 black points in the plane. Think of these as cities. Right? So this is, I don't know, Boston, I don't know, Chicago, Boston, New York City, something like this. And we're interested, and then you specify a radius, and you're interested in all points whose distance sum to the 3 cities is that constant radius. So maybe you're interested in all cities in the US where the distance sum to those 3 cities is 2,800 miles, right? Now, this is an algebraic curve, and this is an algebraic curve of degree 8. And we call this the 3 ellipse, right? And this is the red shape in the beginning. So this in the middle, the black curve, convex curve in the middle is the 3 ellipse for these 3 locations. Now, what about these ellipses? Well, the 1 ellipse is called the circle, and it's an algebraic curve of degree 2. The 2 ellipse is called the ellipse, and it's an algebraic curve of degree 2. The 3 ellipse is an algebraic curve of degree 8. The 4 ellipse is an algebraic curve, 4 cities is an algebraic curve of degree 10. The 5 ellipse is an algebraic curve of degree 32. Okay, so this goes 2, 2, 8, 10, 32, and if you're bored, you can think about how this continues. Okay? But now what happens, right? Let's say we vary the radius. You want to analyze this. You want to know where do you want to build the factory. Maybe you want to minimize this, right? As the radius gets smaller and smaller, the ellipse shrinks, 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 and finally there's a tiny, tiny ellipse, and that's where you want to build the factory, right? That's the factory location that minimizes the distance sum to the 3 cities, right? So you want to, or maybe you replace Boston by, I don't know, something else, right? So then you want to know how does this depend on the data. So if we vary the radius or vary the location of the cities, well, what happens? Is there a discriminant? Is there a case distinction? Yes, right? There's always a discriminant, and you learn that in 9th grade. There's a discriminant, there's this thing under the square root that tells you how your object, how your solution to your problem, to your optimization problem, to your statistics problem, depends on the data. Here's another one. So I spoke about polynomials, but there are many different ways of thinking about polynomials. So one way to think about polynomials is as tensors, symmetric tensors. Well, you know this for quadratic polynomials. So a quadratic polynomial or quadratic form is the same thing as a symmetric matrix. So a quadratic form in 3 variables is the same thing as a 3 by 3 symmetric matrix. Well, that's a form of degree 2. What about polynomials of degree 3? Well, they are 3rd order tensors and so on, right? So if you have a polynomial of degree 6, homogeneous in 3 variables, that's a symmetric tensor of format 3 by 3 by 3 by 3 by 3. Right? So a ternary sextic, a homogeneous polynomial of degree 6, can be thought of as given a function on the 2 sphere. And we might want to maximize this function, and there will be up to 20 local maxima. Well, there'll also be critical points and local minima, and these things are called eigenvectors of the tensor. Well, you knew this from linear algebra, right? If you have a quadratic form, one way this morning in Nikhil Srivastava's beautiful talk, we learned 4 ways to compute eigenvalues and eigenvectors. But another way to think about this geometrically for symmetric matrices is to maximize the quadratic form on the sphere. It's sometimes called the Rayleigh quotient. Same thing for polynomials of higher degree, right? Well, in this example, for a particular polynomial, we see in yellow the landscape, right? This is the graph of our function on the sphere. And you can see there are 20 local maxima, mountains, 12 local minima, and then 30 saddle points, and the Morse complex is the icosahedron. Right? Now, is there a discriminant? Yes, of course there's a discriminant, right? You have these 20 local maxima, but you could have less, right? How many real critical solutions could there be? Well, 20, 18, 16, whatever, right? We need to distinguish the cases, where these critical points are, how many are real, where are they located. We need to distinguish, we need to decide, and for that we have a discriminant. Now, since this concerns eigenvectors, this is called the eigendiscriminant. Well, it's a polynomial. It has degree 150 in the 28 coefficients. It's a big polynomial, but nonetheless, it's one of the many big brothers of the little discriminant you encountered in 9th grade. Now, passing on from this yellow supreme beauty, let me say a word about the SIAM journal on applied algebra and geometry. So this is sort of a header somehow for the community I'm in, and applied algebra and geometry. This journal was started, I think, 7 years ago, and it's going well. And these pictures sort of show you the various domains of application. So at the top, you have the ellipse. So this was the ellipse when you vary the radius as the surface. That stands for optimization. Then one down is robotics, computer vision, topological data analysis, geometric modeling, tensor methods, and then cryptography, the Como surface on the left. Okay, so these are some of the pictures we already saw in this talk. So many varieties, so little time. So what I like to do now, I like to zero in on a particular study involving plane curves, and we'll see one more discriminant, and then we're going to wrap it up. So that's the plan for the next 25 minutes. So the question I like to ask is, how can you draw all possible plane curves of degree 6, well, in the plane, right? How can you make a curve of degree 6? Well, one way you can make a curve of degree 6 is to draw 3 curves of degree 2. Right? So, well, in the left picture, you see 2 ellipses and one parabola. Well, you write down their polynomials, you multiply them together. That's a polynomial of degree 6, and this defines the curve on the left. Right? So that's one particular reducible curve of degree 6. Now, this polynomial, homogeneous in 3 variables of degree 6, has 28 coefficients. Right? So there are 28, so x to the 6th, x to the 5th, y, x to the 4th, So you have how many ways of, you have oranges and bananas and apples, many in a jar, and you can take 6 of them. Okay, there are 28 ways to do this. But now you wiggle the 28 coefficients a little bit, you might get the picture on the right? So on the right side, you have a smooth plane curve of degree 6 that's somehow close to the one on the left, right? But there might be different ways of wiggling, right? How can we distinguish all the possible cases? How can we know how many cases there are? Well, there's a high-dimensional space. There's a 28-dimensional space of coefficients. What are we going to do? Well, we're going to look for discriminant, right? So there is a big discriminant that furnishes the case distinction. So I'd like to tell you a little bit about the geometry of this discriminant. First, a picture. So here are all possibilities, right? So this diagram is a poset, a partially ordered set, and there are 64, actually 56, there are 56 different pictures, and each little picture is an arrangement of real ovals, real pieces of a plane curve of degree 6. Okay? And they're organized by number of connected components. So all the way at the top, there are 11. So circle, the only little circle is an oval. Okay? So at the top, you have 11 ovals, then one down, 10, 9, 8, and all the way at the bottom, you have the empty curve. The empty curve is a very, very important real curve. So for example, if we're in the xy plane, if you take the curve x to the 6th plus y to the 6th plus 1 equals 0. Okay? So there are no real points. But it's a perfectly good real curve. It's a Riemann surface, so if you look at the complex solutions, so what's a real curve? A real curve is a complex curve together with an involution called complex conjugation, and the fixed points of this involution is called the real curve. So x to the 6th plus y to the 6th plus 1 equals 0. There are no real points. We're at the bottom, but it's a perfectly good real curve. If I take x to the 6th plus y to the 6th minus 1, then I'm 1 up. There's 1 oval, and so on, right? So these are the different possibilities, and you can enjoy this picture. And these curves are either red or blue or purple. The purple ones are the ones who can't make up their mind, whether they're red or blue. Okay? Is this clear? Right, so these are the different shapes that a smooth plane curve of degree 6 can have. So I'll explain this picture. Now, first of all, I'd like to say maybe a word. So what we do, for convenience, we're going to do this in the projective plane. So this slide is a little bit warm-up or introduction, a reminder to a projective geometry in the plane. So P2R is the real projective plane, so it's the usual plane together with a line at infinity. Okay? Now, in this plane, we have coordinates x, y, and z. So these are homogeneous coordinates, so every point in the plane has 3 coordinates x, y, z, and that's up to scale. Right? If I multiply them all by 2, then I have the same point. Okay? Now, the simplest curves you could have in the plane are called lines. So a straight line in the plane is the zero set of a linear form. So C1x plus C2y plus C3z, and the c's are not all zero. Okay? So that's a solution set of this equation is called a line in the plane. Okay. Now a question for the audience. So suppose I remove the line from the plane. Yeah, so I take the plane and I remove the line. Is the complement connected or disconnected? Now, if this were a calculus class, I would ask the audience. I would pick a random person in the audience. Now, of course, people in the first row will never get asked, but people in the last row will always get asked. So I'm very tempted, but since it's very bright, it's very hard to see people, so I will not do this. But anybody have a suggestion? So I have this plane, I remove a straight line. Is the complement connected or disconnected? Connected? Okay. Isn't that weird, right? So that's Frank, he wrote a book on this, right? So, okay, so why? You can use the microphone, or is the mic? Yeah? Okay. So this is, so if you take the real projective plane and you remove a line, what's left is the usual plane. Yeah, fine, that's connected. Okay, good. Okay. Let's try this one more time. So let's look at a conic. So we talked about these already. They're green or blue, and they're conic. So a conic in the plane is the zero set of a homogeneous quadratic polynomial. So now I have 6 coefficients, C1 through C6. Now look at the zero set. Now this conic in this plane, well, is either an oval, meaning it's non-empty. An oval means it topologically looks like a circle, right? So like an ellipse. So in the projective plane, there's no distinction between hyperbolas and ellipses. They're all the same. They're only ellipses. Or it's empty, right? So, and this has to do with this 3x3 symmetric matrix. So a miracle of mathematics is that the symmetric real matrices have real eigenvalues, right? So the eigenvalues could all be positive, 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 or negative, 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 in which case the curve is empty, or it's like 2, 1, right? They're both signs in the eigenvalues, in which case it's non-empty. Okay? That's a tiny little discriminant. Okay? Now the second quiz, and not for Frank, is what happens when you remove a conic from the plane. Okay? So connected or disconnected? Disconnected, right? What are the pieces? Okay, that I agree. Yeah? So you have a conic, you have a blue conic in the real projective plane, and you rip it out. And you have 2 pieces in the complement. What are those 2 pieces? Okay, I'll give it a, it's Saturday, and it's been a long. One is called a disk, and the other one is a Möbius band. Right? So topology is interesting. There are 2 different parts. There's the interior. That's topologically a disk, and there's the exterior that's a Möbius band. Okay? And Ruth is nodding, so you can ask her why. Okay? Okay, so very good. So we have all these ovals in the plane, and the ovals have an interior, and the interior is the disk, and the exterior is the Möbius band. Well, let's see what we can do with this. So, okay, first a few happy words of algebra. So there is a discriminant, right? So this is a polynomial of degree 75 in the 28 coefficients. And there's an explicit formula. So there's a very nice, essentially 75 by 75 matrix where you sprinkle the coefficients into this matrix, and then the determinant of this matrix is our discriminant. Okay? Now, if you were to expand this, it's going to be a big polynomial, but so it's a discriminant. It's a very nice polynomial. It discriminates, so we can't give a formula. Now here's a theorem, right? So this, what I'm talking about, is Hilbert's 16th problem, and this asks to classify algebraic curves, and particularly he was interested in algebraic curves of degree 6 in the projective plane. Many people worked on this, and this was culminated in the following classification theorem. It's known as the Rochlin-Nikulin classification, and it says the following. So if we take the hypersurface of the discriminant in projective 27-dimensional space. So I have this big polynomial. It carves out a hypersurface, and we're interested in the connected components of the complement. Then this says there are 64 connected components. So those are the smooth types of curves. These are called rigid isotopy types. So these are the types that rigid isotopy means that if I have a curve and you have a curve, they're the same type. If I continuously deform my curve into yours, with all curves in between being smooth, no singularities. Okay? There are 64 types. Now, these map to 56 topological types. So topological type means the following. So I have all these circles in the plane, and if I have a curve and you have a curve, they have the same topological type if there's a homeomorphism from my projective plane to your projective plane that takes my curve to your curve. Okay? Now, it's easy to see that rigid isotopy implies topological equivalence, and the converse doesn't hold, as we see here. So let me refine this. So here's the picture back. So let me now I'm ready to tell you what's the distinction between blue and red, and who are these 8 guys who can't make up their mind, right? So there are 56 topological types of smooth plane sextics, and they are shown in this poset. 42 are called non-dividing, and they are blue. 6 are called dividing, and they are red. And 8 can't make up their mind. They can be dividing or non-dividing, so they come in 2 topological types. This explains the difference, and this accounts for all 64 connected components in the complement of our discriminant. Now, what's dividing? Well, remember, a real curve is a Riemann surface, a complex Riemann surface, together with an involution called complex conjugation. So you remove the fixed point locus from the surface, then the complement is either connected or not. Right? So if you remove the real points from the Riemann surface, then either there's one connected component afterwards or 2. And if there are 2 connected components, called dividing. If there's only one connected component, it's called non-dividing. Okay? So then now I think I explained everything in this corollary. Right? So this corollary explains this picture. Okay? And on top, these maximal curves or M curves, they are always dividing. They're red. And then the purple guys, they come in 2 flavors. So each purple curve comes as a dividing or non-dividing type. But how do we distinguish these curves? Let's say one of these curves walks into the door right now with all of its 28 beautiful coefficients. What should I do, right? Which of these types is it? Well, I need to discriminate. I need to distinguish. I need to discriminate. I need a program that tells me that, and that's why discriminants are nice. Let me tell you a little bit about this poset. So in this poset, we can go up and down, right? So there are these edges, they're covering relations. So you have a curve with a certain number of ovals, and if you go up, there's one more oval. If you go down, there's one less oval, or you could stay in the same level, right, and keep the so how do you do these transitions, right? So I'm zooming in on a little piece of the curve, and the theorem says for curves of even degree in the plane, and 6 is an even degree, every transition, discriminantal transition, is one of the following 3 things. Okay? So what do I mean by a discriminantal transition? So the discriminant is a hypersurface in our data space. Our data space is carved up into many components, these types. And discriminantal transition is if I cross this wall generically once. So if I'm on one side and you're on the other side of the wall, and I go through precisely once transversely, I'm going to call this a discriminantal transition. I just walk through the wall one time. Okay? So the following 3 things can happen. Well, you can either, so this is from top to bottom. So let's say I go from one level, I go down by 1. Either I can shrink an oval and make it disappear. Right? So you could imagine you have one of these ovals, I change the coefficients, the oval gets smaller and smaller and smaller, it becomes a point, and poof, it disappears. Right? This is called shrinking an oval. That decreases the number of ovals by 1. Another thing that could happen is called fusing of ovals. Right? I might have two ovals, and they come together. They come together, they come together, they beep, they touch each other, and they make one oval. Right? That's the second thing. And these are the covering relations. And in fact, for each of the edges in the poset, I can realize this. So if Tom picks an edge, I can make a curve upstairs and a transition that does either of these two things. Okay? Now, more interesting are the horizontal transitions. This is called turning an oval inside out, and this is visualized here. Right? So this is a curve that has 5 connected components. One is drawn as an unbounded component. And what I'm going to do, on this unbounded curve, I'm going to turn the oval upside down, inside out. Right? Well, what do I mean by this? You can see how this sort of comes together, right? This oval, I mean, this is a single connected component that comes together, and then there's this restructuring, right? And then you have the other type on the right-hand side. Now, what happened to this particular connected component? Well, on the left picture, viewed from you, on the left picture, what you see as inside is the inside, and what you see as outside is the outside. But as you go to the right side, this flips. What you see in the middle is the outside, and what you see up and down is the inside. Now, how do you distinguish the inside from the outside? Well, the inside is the disk, and the outside is the Möbius band. Right? So there's always, an oval has 2 connected components when you remove it, and this is these horizontal transitions, and again, you can always realize this. So this is the geometry of the discriminant. These are the different ways of walking through the discriminant and traversing our poset. Now, I'm a little bit too late, but maybe not too late, right? So let me use the same poset turned upside down to wish you a very, very happy new year, 2023, right? So this is the very same poset, but now the M curves, the maximal curves are at the bottom, and the empty curve and so on are at the top. So this is, again, our poset. Now the transitions are in green, the discriminantal transitions that were described by this theorem. Okay, so that's my season's greetings. I have 7 more minutes. I have a little more to go. 5 moments. Can I just a little more? Okay, a little bit more. We're almost done. Okay, the conclusion. So let me conclude. Okay. So the conclusion is this talk was about the quadratic equation, ax squared plus bx plus c equals 0. This has 2 solutions, x, and there's a formula. And the single most important ingredient in this formula is this tiny little thing under the square root. It's a discriminant, b squared minus 4ac. Even if you cannot remember the formula, I certainly cannot remember the formula, please remember there's a discriminant. The discriminant tells you this, it carves up data space into regions. And this is a qualitative distinction. It discriminates. So it characterizes the case distinction for the nature of the solution. So in this small high school case, 2 real roots versus no real roots. Now, discriminants are everywhere. You see them often along with supreme beauty. They're very, very important and beautiful, not just in 9th grade. Thank you very much, and this was it.
Thank you for an extremely entertaining and interesting talk. So let's thank Professor Sturmfels again, and also I want to present you get an official something.
Okay.
Is the photographer here?
Maybe somebody has a cell phone.
Yeah, there was a photographer here.
Okay.
Okay.
Well, thank you very much. This was fun. Thank you so much. Thank you.
I guess, I don't know if there are questions. I don't know.
I'd be happy to, if there are questions.
Oh, there's a question.
Okay. Since I have a flight coming up and I'm going to need something to compute on the plane on the way home. So I apologize if you didn't answer this, but if a real curve of degree 6 walks in, I have these 27 coefficients. The discriminant doesn't tell me which.
That's correct. You need a bit more information. So
how do I do that?
Yeah, you need additional inequality. So I swept this under the rug. So here the simple answer is we wrote a Mathematica program that does that. So if your computer on the plane runs Mathematica, you can download a piece of code that will eat your 28 coefficients and will tell you which of the pictures you have. But in this implementation, of course, the discriminant is enhanced with additional information. So you need more inequalities. So it's more complicated, of course, in one variable, and there's only this one inequality. But the main point of the discriminant, so the highest degree, sort of the most significant contribution comes from the discriminant, but then there are additional inequalities that are sort of supplementary that you also need.
I don't know if it's on. On the picture where you flip the oval inside out, can we think of maybe like a saddle point at that interchange?
Yeah, I think so. I think there's sort of that kind of topological changes you see, catastrophe theory are very much like that. So you can see, at the in-between state, right?
Are there sort of singular versions that would live in between them, or is that not showing up in the algebraic geometry?
Yes. So in between, the discriminant becomes 0, right? So the discriminant on the left-hand side is positive, on the right-hand side it's, negative, but there's a unique point in between where it's 0. And you can compute this point up to 10,000 digits reliably. And you know why? Because I gave you a formula for the discriminant, right? So not only is there a point in between, you can find it up to as many digits as you want very fast.
So in the Rocklin-Nicolin classification, the first part of it is about the number of connected components in the complement of the discriminant. So what is a good way to do such a count?
Oh, it took many years. So it's quite non-trivial, right? So the way this works, you first sort of make an overview, a combinatorial classification, what might the possibilities do? And that was already done by Hilbert and others in the 19th century. So maybe they drew a whole bunch of pictures like this. So somehow you say, well, how could this look like, right? And here are 120 pictures, right? Now then you slowly eliminate cases. You say, well, this picture is not possible because some topological invariant has this property or that property, and then you wiggle your way down, and eventually you get down to a conjectured list of 64 pictures. But now you have to realize them all, right? And then you have to find, maybe you already know 62, but 2 of them are undecided. And in fact, this is a very special case. So the top guy in the middle, Hilbert got wrong. So Hilbert in his paper said that this type does not exist. And this was shown in the Russian school in the 1960s, was actually shown to exist. So then at some point you have to construct them. And the ultimate construction, the ultimate proof is quite deep. So I should maybe say for the algebraic geometers, a plane sextic curve is really a K3 surface. So the double cover of the plane ramified at the sextic curve is a K3 surface. So you really need the full force of the global Torelli theorem for K3 surfaces to prove this. So it's quite a deep theorem. So you sort of have an upper bound, which are pictures. You eliminate pictures. Then you have to kind of go up and realize them. And to sort of really decide the hardest cases, you need quite a bit of algebraic geometry.
Thank you.
Okay, well, gave us all something to think about on our trip home, so thank you very much.
Thank you.